Hello students, in this video we look at some more methods to solve ordinary differential equation of order 1 but not of degree 1. Here we'll discuss Lagrange equation when a given differential equation is in some particular form. The Lagrange differential equation is given by y is equals to x, some function of p, plus some function, another function of p, x into some function of p plus f function of p. Then this type of equation is known as Lagrange equation. Here p is dy upon dx. This is a first order but not a first degree ordinary differential equation. Here we also look the given differential equation, the degree of dependent variable y is 1. One method which is solvable for y we have already discussed, in which also the degree of dependent variable y is 1. In that case, we solve problem by differentiating this equation with respect to x. So similarly, we will differentiate this equation with respect to x and further we proceed. So first we differentiate this given equation with respect to x, hence we get dy upon dx becomes p, and in right hand part derivative of x gives us 1, so it gives us f of p plus derivative of fp is f dash p into dp upon dx plus derivative of f is f prime p into dp upon dx. Now we will shift fp into left hand part, so we get p minus fp is equals to, in right hand part taking dp upon dx from these both terms outside, so we get x f prime p plus f small prime p dp upon dx. From here we can rewrite this equation as dx upon dp. So shifting dx upon dp into left hand part and divide this equation by p minus fp, we get in right hand part x f prime p plus f prime p upon p minus fp. Now further we can rearrange this equation as dx upon dp minus x into f prime p upon p minus fp equals to f prime p upon p minus fp. This is a linear differential equation of order 1. Here x is dependent variable and p is independent variable. So from here we can obtain a solution between in x, p and c. So from here we get a value of x in terms of p and c. Now we will put this value of x in given equation, which is equation number 1. So when we put here x from obtained equation 2, we get another result, y is equals to some function of pc f of p plus f of p. This is again a relation between y, p and c, or y is equals to some function of p and c. So equation number 2 and equation number 3 together gives us a solution in parametric form where p is in parameter. So if given equation is in Lagrange form, we can obtain the solution of a given differential equation in parametric form. So look here, we have a problem y is equals to a px plus bp cube. So first we differentiate it with respect to x. We obtain p is equals to ap plus ax dp upon dx plus 3b p square dp upon dx. So first we shift ap into left hand part and taking dp upon dx from last two terms outside, so we get 1 minus ap is equals to ax plus 3bp square dp upon dx. We can rewrite it in the form of dx upon dp, and further we rearrange it dx upon dp minus a upon 1 minus ap into x is equals to 3b upon 1 minus ap. So this is a linear differential equation in order 1. So to solve a linear differential equation in order 1, first we have to find integrating factor, which is exponential. This is exponential integration integration with respect to independent variable, which is p. So we get integrate exponential of minus a upon 1 minus a p dp. Its integration we will get exponential a upon 1 a minus 1 log p. Taking minus outside, so here we get a upon a minus 1, and integration of 1 upon p with respect to p is log p. So we can rewrite it as p raised to power a upon a minus 1. And now the solution of this equation can be written as x into integrating factor, which is p raised to power a upon a minus 1, is equals to right hand part, which is exponential, which is 3b p upon 1 minus a, into integrating factor, which is p raised to power a upon a minus 1, integration with respect to p, plus c is arbitrary constant. Now we solve this term. So first, taking p raised to power a upon a minus 1 and p raised to power 1 together, we get p raised to power 1 plus a upon a minus 1. When we solve it, we get p raised to power 2a minus 1 upon a minus 1. Now we will integrate it with respect to p, hence we get p raised to power 2a minus 1 upon a minus 1 plus 1 upon 2a minus 1 upon a minus 1 plus 1. Now we solve this, simplify this term. After simplifying, we get p raised to power 3a minus 2 upon a minus 1 upon 3a minus 2 upon a minus 1. Here this a minus 1 cancel out, so here we have a negative sign, so it becomes 3b upon, again taking minus outside from here, so it becomes 2 minus 3a. So 3b upon 2 minus 3a into p raised to power 3a minus 2 upon a minus 1 plus c. And in left hand part we have x into p raised to power a upon a minus 1. So from here we can obtain the value of x, which is x is equals to 3b upon 2 minus 3a into p raised to power 3a minus 2 upon a minus 1. Now we will multiply this whole equation with respect to p raised to power minus a upon a minus 1. So here when we solve this expression, we obtained p raised to power 2. When we solve this, taking a minus 1 LCM, so we get 3a minus 2 minus a, it gives us 2a minus 1 upon a minus 1. Hence here we get p raised to power 2. And second term is c p raised to power a upon a minus 1. So this equation becomes x is equals to 3b upon 2 minus 3a p square plus c p raised to power a upon 1 minus a. This is second equation. X is equals to some function of p and c. Now we will put this value of x from 2 to 1, which is given equation. So we obtain, in given equation we have here y is equals to apx. So when we put x from 2 to 1, we get a into 3b upon 2 minus 3a p cube into ac p raised to power a upon 1 minus a plus 1 plus bp cube. This is a term appear in equation number 1. Now we will simplify this expression. Hence we obtained y is equals to 2b upon 2 minus 3a p cube plus ac p raised to power 1 upon 1 minus a. This is y is equals to some function of p and c type equation. So the equation number 2 and equation number 3 together with gives us a solution of given problem in parametric form. Now discuss one more form, this clairaut form. Clairaut form is also a specific form of Lagrange equation. In Lagrange equation we have y is equals to x into some function of p. If this function of p is p only, it means p raised to power 1 type term only, then it becomes y is equals to xp plus function of p. So such type of equation is known as clairaut form. In Lagrange form, when we replace f capital F of p with p, so it becomes y is equals to xp plus function of p. This is known as clairaut form. So As we solve Lagrange equation, similarly we have to solve clairaut form. When we differentiate this with respect to x, we obtained p is equals to p plus x dp upon dx plus f prime p dp upon dx. Here p cancel out. So remaining term is x plus f prime p dp upon dx. Because x plus f prime p cannot be 0, it means dp upon dx must be 0. So from here we obtain p is equals to some arbitrary constant. It means in clairaut form, to obtain the solution, we can just replace p with some arbitrary constant c. Hence, we get y is equals to cx plus f of c. This is a required solution. So let's have a problem. Y minus px into p minus 1 is equals to p. First we rewrite this as y minus px is equals to p upon p minus 1, or we can rewrite it as y is equals to px plus p upon p minus 1. So this is what y is equals to px into some function of p. This is clairaut form. So in clairaut form, just we are to replace p with some arbitrary constant c. So the solution of this problem using clairaut form can be written as y is equals to cx plus c upon c minus 1, where c is some arbitrary constant. Let's take one more problem. We have dy upon dx whole square into x square minus a square minus 2 dy upon dx plus x into xy plus y square minus b square is equals to 0. First we write dy upon dx as p here. So it becomes p square x square minus a square minus 2pxy plus y square minus b square. Now taking first, third and fourth term together, it becomes p square x square minus 2pxy plus y square. This is what? Y minus px whole square. Now the remaining terms, which are p square, a square and b square, shifting them into right hand part, we get y minus px whole square is equals to p square a square plus b square. Now taking square root both side, we get y minus px is equals to plus minus square root of p square a square plus b square. So square root of this we obtain. So when we or we can separate it as y minus px so it becomes y is equals to px plus p square a square plus b square raised to power half. So similarly, here we have y is equals to px minus p square a square plus b square raised to power half. Now these are clairaut form. So here simply we will replace p with c. So we get y is equals to cx plus c square a square plus b square raised to power half. So, or we can rewrite it as y is equals to cx plus minus this power half, or shifting cx into left hand part, we get y minus cx raised to y minus cx is equals to plus minus c square a square plus b square. Now squaring both side, then we get y minus cx whole square is equals to c square a square plus b square. This is a required solution. So in this way we are to use clairaut form to obtain solution of ordinary differential equation of order 1 but not of degree 1. So that's all about